Hey guys, welcome back. This is going to be the notes for AP Circuits Part 3. So AP Circuits Part 3. One of the things that we're going to have to be able to do is to combine resistors. And the idea is that we can simplify a circuit very much like how we simplified a vector by breaking into components. We can simplify a circuit by combining those resistors into another resistor. So we take multiple resistors and we say, okay, I could replace all of these resistors in a circuit with one. And I would still have the same circuit. Everything would be unchanged. And that's our equivalent resistance or our total resistance. So it could either be an R with the subscript of TOT or an R with the subscript of EQ. So if the resistors are one after another, if they share a path, to add them, you just add them. You're just going to add the values together. So my R total is going to be equal to R1 plus R2 plus R3. On your equation sheet, this is going to say RS for series, and it's going to have a capital sigma, an R, and a subscript I. So it tells us that we're going to take a summation of resistors. They share a current in this, so they're all going to have the same current when they're in series, which would be important for us solving problems. A common example of this is how Christmas lights used to be, where if one of them would burn out, then the entire line wouldn't work anymore. All right, so first example. So we have two resistors in series. Really easy. I have a 500 ohm resistor. I have a 450 ohm resistor. If I wanted to replace those two resistors with one and then have the circuit still be the same, still behave the same, I would take 500 plus 450 and I would get 950. So a 950 ohm resistor would replace those two. All right, so we have R1 and R2. R1 is 10,000 and R2 is 1,000. So my R total is going to be 10,000 plus 1,000 or 11,000. And the idea is you could put an 11,000 ohm resistor in this circuit and it would behave the same. All right, now if you have multiple paths, so the current's going to split. So you could take one of those resistors out and you would still have a closed circuit. It's going to make it easier for the resistance to go. So when they're in parallel, whatever the resistance is going to be less than the least. So the way that I would explain this if we were in class, I'd say, okay, there's an emergency. We have to get out of the room. In series, we'd only be allowed to use one door. And so all of us have to go in the same way. If I open up the door to the back of the room and some of us can go one way and some can go the other, the room's going to empty faster. So that's what parallel is like. It's 1 over R total equals 1 over R1 plus 1 over R2 plus 1 over R3. On your equation sheet, it's going to say 1 over Rp is going to be the summation of 1 over Ri. It is more convenient for us, for the sake of how we're going to put it into a calculator, to say that resistance in parallel is 1 over R1 plus 1 over R2 plus dot, dot, dot. Because that's how you would actually input it into your calculator. They're never going to ask you for 1 over the parallel resistance, right? They're going to ask you what the parallel resistance is. All right, so I have a 100 ohm resistor and a 50 ohm resistor, and these are in parallel. I like the way this is drawn. I drew it myself because it's parallel in the case of circuits, but not parallel in the case of math, right? Now, sometimes both of those things will be true. So the current comes out of the battery, and we're saying that it's conventional current. The current goes into the battery. These two are the same. So the battery is not providing any electrons. The battery is just pushing what's already there. Everything you're attaching a battery to is already full of electrons. When it gets to this junction, it can split. And some of it can go this way, and some of it can go that way. So that's what makes these parallel. The fact that some of the charge can go either way, and individually they provide their own path. So I'm going to say that our parallel is going to be 1 over R1 plus 1 over R2. So in your calculator, you'd put it in like this. 1 divided by parenthesis, 1 divided by 100 plus 1 divided by 50, close parenthesis. And that's going to give us 33rd and a third. So we're saying that we would get the same thing. And again, like I said, it's going to be less than the least. So the least resistor in our system before this was 50. It's going to be a little bit easier than that. Now it's 33 and a third. I could put a 33 and a third in here, and you'd have the same circuit. It wouldn't change anything. All right, so if I have a 200 ohm and a 100 ohm, the same thing. I'm going to have 1 divided by 1 divided by 200 plus 1 divided by 100, close parenthesis. And I think this is 67. 66 with the repeating 6. But why don't I do it in the calculator, just since I have a calculator here? Yeah, I get 67 if I round up. And it makes sense to round up with the resistance, because if you have a real resistor, as we're going to see, that last line is telling you what the tolerance is, what they're guaranteeing it to. So they're only saying it's so close to a certain thing. All right, now you could have both series and parallel. So in this picture here, between those two reference points, R1 and R2 are in parallel, and their equivalent is in series with R3. So the first thing that I'm going to do is I'm going to replace R1 and R2. What am I going to call this new resistor? I'm going to call it R12. And I'm going to say that R12 is 1 divided by 1 over R1 plus 1 over R2. So this is 50 and 1 over 50, and it's going to be 25 ohms. So it turns out if you have two of the same resistors in parallel, their equivalent resistance is half of their resistance. If you have 3 of the same resistors in parallel, their equivalent resistance will be a third. If you have 4, the equivalent resistance would be a fourth, and it would keep on going as long as they're the same resistance. All right, so I can redraw this because I'm saying that it doesn't change. And now I would redraw this as I have R3, and now I'm replacing R1 and R2 with R12. And now these are in series. So that means that I just need to add them together. And I'll call this R total, but I could have easily called it R123. And that's going to be equal to R3 plus R12, which is 50 plus 25, or 75. And so again, the idea is that one 75 ohm resistor would completely replace all of those other ones. All right, so all of these are 10 ohms. I want to get the resistor that would replace all of them. So I'm going to combine these two together as R2, 3. And I'm going to combine those two together as R4, 5. If we look at what is happening with the current, I'll switch colors so it makes more sense. The current is leaving the battery as the green arrow. The same current is entering the battery as a green arrow. These are equal, and then they are splitting. So some of it is going up top. This path just through R1. Some of it is going through the bottom, which is that path through R2, 3. Then it's going to come back together briefly at that junction, and then it's going to split again. And some of it is going to go through R4, 5. And some of it's going to go through R6. So these are in series because they share a path. All right, so now I have a new circuit, which I'll redraw. And you don't have to do this every time you do it, but we're starting out. So I'm going to say, okay, I have R1 and I have R2, 3. I have R4, 5. And I have R6. And I'm saying that this circuit would behave exactly the same as that circuit. That's what it means when you have an equivalent resistor. All right, so now I have parallel components. I can combine R1 and R2, 3, because R1 is in parallel with our new equivalent resistance, which again is imaginary like components, but it helps us to solve it. And I'm going to call the combination of R1 and R2, 3, R1, 2, 3. And so I'm going to say R1, 2, 3 is going to be 1 over R1 plus 1 over R2, 3. And so this is going to be 1 over 10 ohms plus 1 over 20 ohms, which is going to be 6.7 ohms. And I'm going to do the same thing with R4, 5, and R6. I'm going to call that R4, 5, 6. And that's going to be 1 over R4, 5 plus 1 over R6. And so I have 1 over 20 plus 1 over 10, which is 6.7. All right, so now I had started with 6 resistors. I'm down to 2. I'm going to redraw my circuit again. And again, you don't have to do this every time. And I'm just trying to make it show you what these things mean. So when I redraw this, I'm going to have R1, 2, 3 and R4, 5, 6. And I know that this one is 6.7 ohms, and this one is 6.7 ohms. And so my total, which I could call R total, or I could call it R1, 2, 3, 4, 5, 6, is just going to be R1, 2, 3 plus R4, 5, 6. So it's going to be 6.7 plus 6.7 is 13.4. All right, so let's review. What does series mean in a circuit? It means that they share a path and that they have the same current. What is the equation for series. I'm going to write it like it is on the equation sheet. And it's going to be R of S is equal to sigma Ri. What is parallel? Parallel means that the current is split and they have independent paths. What's the equation? I'm going to write it as it appears on your equation sheet, and I'm also going to write it as is actually useful. What's an equivalent resistance? An equivalent resistance is a resistor. Be helpful if I spelled resistor right? A resistor that takes the place of multiple resistors without changing the circuit. So what we're going to do with this is once we replace it with this, we're going to get some information and we're going to go back to the original circuit with it. So that's what we're trying to find out information about the circuit. All right, so looking at this, is anything in series? Yes. Those two share a path. So what am I going to do? I'm going to combine the 4 and the 2 as a 6. Anything else in series? No. But these two are in parallel and those two are in parallel. So let me combine those. So I'm going to have 1 over 8 plus 1 over 6. I got about 3.4. And I have 1 over 6 plus 1 over 4. I think it's 3. No, 2.4. All right, so now I replaced these two with a 2.4 ohm resistor, and I replaced these three with a 3.4 ohm resistor. Now the 8 and the 3.4 are in series, and the 6 and the 2.4 are in series. So this becomes an 8.4. This becomes an 11.4, and now the 11.4 and the 8.4 are in parallel. And so I have to do the 1 over. You would think they would have picked rounder numbers. I didn't make this up, so we can't blame me for this one. I got 4.8. All right, I'll give you guys a second to figure out what this is, and I'll quickly go through it. So it shouldn't take you more than 2 minutes to do it. The answer should be 25. All right, so I'm going to start combining things. Is anything in series? Yes. There are 3 things in series. R6, R1, and the battery. R1 and R6 could be replaced with the 20 ohm. Anything else? No. Anything in parallel? Yes. 2 10s. Remember I said if they were the same resistor, they could be replaced with half. They're 5. Now I have a 5 and a 5 in series. 5 and a 5 in series is going to give me a 10. Now I have a 10 and a 10 in series. A 10 and a 10 in series is going to give me a 5. Now I have a 20 and a 5 in series, which is going to give me 20 plus 5, 25 ohms. Or 10 plus 5. You don't have to combine these right off. But these are in series. These three things are in series. Even though this isn't a resistor, it's also in series. What does it mean to be in series? It has the same current. So the same current's going through the battery that's going through R1 and R6.